Hi everyone and welcome to this video on integration by substitution. This is a type of question that comes up fairly regularly throughout the specialist maths course and also is commonly used at higher levels of maths. So if you're going on to a tertiary level to study maths or anything like that, this process again comes up quite frequently. And basically this is a process which enables us to solve integration problems that really we wouldn't be able to do otherwise without the use of technology or that sort of thing. Because just looking at them, they're kind of nasty. Now, what I'm going to sort of point out is if we have a look at the very first question that I have written here. So the integral of tan x times sec squared x, just here. The thing that we have to kind of notice here is that we have a function being multiplied by its derivative. Okay, and that's one of the sort of situations where we can use this process. Now, what we basically do in this situation is we make u equal the original function. So in this case, I would say let u equal tan x, and that means that du dx must be sec squared x. So then I can actually rewrite this integral and say, well, that's really just the integral of u times du dx, and then we've still got a dx on the end. But you can kind of think of it as the dx is basically cancelling each other out, and so we're left with the integral of u du, which that's fairly easy to evaluate. So just integrating that, we'll get u squared on 2 and then plus c. And then when we put our original function back in, we'll end up with tan squared x on 2 and then plus c. Now that would be sufficient to leave that just there. However, I will say that if you use your calculator, you do get a different answer to this. So the calculator will tell you that it's 1 over 2 cos squared x. So basically half sec squared x plus c. And so I wanted to actually just show, how we could go that step further. So just so you're aware though, that is the end of the question right there. If we wanted to take it that one step further, we can use the identity which says sec squared x equals tan squared x plus 1. So that means that tan squared x would be sec squared x minus 1. Now, if I make that substitution into the rule here, then I'm going to get sec squared x on 2 minus 1 on 2 and plus c. But the thing is, when we have minus half and then also plus c, well, that's still really just a constant. And so the thing is, I could actually just write that as sec squared x on 2 and then plus d. Notice that the constant there has changed from what we had originally, so I should use a different letter for it. But yeah, that's how you can arrive at the answer that the calculator gives as well. Now I will do this other example here, and this is the only other example I'm going to do on this video. I'm going to do another video following up with some more complicated questions. So in this one here, we need to notice that the 4x squared is pretty close to a derivative of the x cubed. And so I can say let u equal x cubed, which means that du dx must equal 3x squared. Now the thing is, here I've got a 4x squared, so I need to actually multiply this 3x squared by something to make it into 4x squared. So I could say, therefore, that 4x squared is actually just 4/3 of 3x squared, because the 3's would cancel each other out, which means that that is actually just 4/3 of du dx. So now I can substitute that back into the original problem. So it's the integral of, now the 4x squared, I'll write it as 4/3. I'll put the du dx over here because the order that we're doing these in doesn't matter. We're just multiplying these things. Then we've also got e to the power of u, and there was a dx on the end of that. Now again, the dx's cancel each other out. And so we're doing the integral of 4/3 e to the u, which works out just to be 4/3 e to the u, and then plus c. And so making the substitution back into this, we end up with 4/3 e to the x cubed plus c. And there we have it. Anyway, I will leave that video there and see you in the next one.